So we just found a closed-form solution for the inverse kinematics of a two-link robot. You can't help but wonder that as the robot gets more complicated, finding closed-form solutions is going to get more challenging. Take this RRP, RRR robot. We specify, again, these 16 numbers. Really, they're 12, because we know the bottom row will always be 0, 0, 0, 1. So we have these 12 numbers over here. We equate it to the forward kinematic map, and we have these 12 equations and 6 unknowns. This can be an incredibly difficult problem to start to solve algebraically or even geometrically. So what we're going to do is we're going to start to add to some of our tricks to see when we can solve a problem in closed form, because we could solve in closed form, that's very desirable, because once we have the closed form solution, not only do we understand it, but it's also easier to implement on a robot, and the implementation will run a lot more quickly. So another way we can come up with closed form solutions for some robots is the so-called kinematic decoupling. What we're going to do is we break the robot down into two parts. First, we'll call it the base or the front of the robot, and the second part is the wrist of the robot. What we're able to do is we figure out the orientation of what the wrist should be. From there, we then get a position of where the center of the wrist should be, and then we have a more conventional inverse kinematics problem that just gets us from the base to some point in space. We're going to do 3 examples of kinematic decoupling. A simple planar 3-link robot, the SCARA arm, and then finally a 6-degree of freedom robot that has a spherical wrist. So here's the 3-link robot. Length 1, length 2, length 3, 3 joint variables. This inverse kinematics problem is posed given a position and an orientation of the end effector. Tell us what the joint variables are. Now, I remind you, the joint variables are measured always with respect to the previous link. The position of the end effector is always with respect to some global frame. And then the orientation of the end effector is, imagine you have a vector emanating from the last link. The angle that vector makes with the horizontal, in the planar case, is the orientation of the end effector. It turns out this problem is easier than you think. 3 degrees of freedom. You have 3 things you specify. What we can do is just take the last link and lay it down in such a way that the position that we prescribed is where the end effector is touching, and orient this link such that we're at the orientation that was prescribed by the inverse kinematics problem. Now, what we have is a simple 2-link inverse kinematics problem where we want to position xc, yc, the center of the tool, if you will. That's a pretty straightforward problem. We just did that. And then finally, once we have our theta 1 and theta 2, as well as the orientation of this last link, it's very easy to figure out what the theta 3 joint variable should be. And that's the solution to the 3-link robot. It's pretty straightforward.